Hey, I'm Vince Conrad. I'm with RJ Lee Group, and where I'm a consulting scientist and sometimes a manager of business development for oil and gas. Okay, I do a lot of work for oil and gas, but I also do work with mining and other energy entities. What I'm going to talk today about is characterizing scales and deposits. But before I do that, I just wanted to have a couple of obligatory slides about RJ Lee, introduce who we are. We're a materials characterization industrial forensics laboratory. Okay, we specialize in problem solving, consulting, and we do a lot of technical support for litigation, and we do some contract research. We've been around for about 30 years. We have a fully equipped laboratory to support the projects that we're working on and our clients, the work that our clients provide to us. And we're certified for a number of different services and we provide compliance services. These are some of the expertise that we have in the areas that we work in. You can see they're quite varied. It's not just oil and gas or energy. We have scientists in a broad array of areas. And these are some of the industries served, including the ones in red are certainly represented among us here today. Okay, so that's my obligatory couple of slides. We'll get into the scale and deposit characterization part of my talk. I think the first thing that I want to do is define what I call a scale and what I call a deposit, because I look at these a little bit differently. A scale is when you have mineral precipitation, when solubilities exceed either in the water or sometimes at a surface, a hot surface, a vacuum surface, where you can get increased concentrations of anions or cations. Some common scales that Steve talked about, you've already heard, carbonates are very prevalent and sulfates are prevalent in the oil and gas industry. One thing that you'll see for any of you that are in the water treatment, I know a number of people here are today, as you get into evaporators and higher temperatures, you'll start to see some silicates form, particularly some magnesium silicates and some other difficult scales. A deposit, what I call a deposit, is just accumulation of particles. Okay, they may be related to a scale. It might just be debris from corrosion. It might be sand particles. Whatever collects together and restricts flow or impedes production, called a deposit. Now, often when you'll see the two forming together, you may have some sand particles, as Steve mentioned, some corrosion particles, and they're kind of bound together with some calcium carbonate. So if you've got both of these things occurring, then obviously you're going to have a little bigger problem. Scales and deposits can form in all phases of natural gas development utilization. I've seen scales from all of these situations over the past 3-4 years. You certainly see a lot in production, and you certainly see a lot in water in the business, both in the utilization and treatment. But I've also seen it coming out of pipelines. I've seen it in processing plants and different times, different scales and deposits. I won't spend too much time on this because Steve kind of covered it already. There are some factors that affect scale production. pH, you can see this is a solubility curve for calcium carbonate. You can see as pH goes up, the solubility goes down by orders of magnitude. Sometimes the pH can affect these things a whole lot. And I suspect that Pat will be talking about this a little later. Temperature can affect scales in all different types of ways. Sometimes it makes them more soluble, sometimes it makes them less soluble, sometimes it will peak out, and as the temperature rises, it will get less soluble. You really have to look at it on an individual basis. Another important question is what's in the water. If you have lots of chlorides, pretty soluble. You're probably not going to have a whole lot of scaling from the chlorides. But if you've got sulfates, if you've got carbonates, more prone to forming scales. Ionic strength, again, is an important factor. As the ionic strength of the water goes up, typically the solubility of any particular scale will also go up. So I think this is one advantage we have now with recycling water and using brine water, is that you're probably going to have a little less scaling because of the high TDS you have in that water. And of course, velocity, whether it's in a fluid or whether it's an air type situation, if you have high flow, it's harder for the scale to adhere to whatever substrate it's going to adhere to. And the problems that are caused by scales and deposits are typically bad. Not all the time. Sometimes you want a little bit of scale. If you get a little bit of a carbonate scale, it actually forms a protective coating on pipes and other metal surfaces, but you don't want very much. Okay, when you start getting lots of scaling is when we start having problems. It causes loss of heat transfer, causes heat exchangers, various types of system inefficiencies, flow restrictions, and you've all seen these where you take a pipe out of service and you wonder how anything is getting through it. Certain types of scale can promote corrosion, and of course, the summation of this is you can have some unscheduled equipment outages. Okay. So, why do we want to characterize scales and deposits? What customers that I work with see is that as they identify the type of scale and deposit they have, it gives them an understanding of why the scale formed. And if you can get an idea of why the scale is forming, then you can start getting a feel for, okay, what kind of issues might that particular scale cause as time goes on. And you can start looking at ways to eliminate it and steps you might take to mitigate formation in similar type instance or in that particular instance in the future. Now, many of you have been in this industry for a long time, and you might think, okay, I look at these type of situations all the time. I can tell a carbonate scale from barium sulfate scale from something else. And that may well be right if you have lots of experience. What I see is probably 60–70% of the time when I get scales to characterize and the customer thinks it's one particular thing, it turns out to be something else. So sometimes it's not quite as straightforward as you might think. Sometimes we know what we know, sometimes we think what we know, and sometimes we don't know. And this is much better said by Donald Rumsfeld. Donald, when he was Secretary of Defense, had this famous quote which said, "There are things that we know that we know. There are known unknowns." That is to say, there are things that we now know we don't know. But there are also unknown unknowns. And there are things that we do not know, we don't know. And each year we discover a few more of those unknown unknowns. Now, as discombobulated as that is, there's some truth in there somewhere, I think. And certainly in these last couple sentences here, there are things that we don't know, we don't know, and each year we discover a few more of those. And certainly that applies to this industry because of its infancy. We're learning things on the fly every day, better ways to handle things and to move on and get better production. So my job today here is to try to help you turn your known unknowns and unknown unknowns into known unknowns by characterizing scale deposits. I hope I said that right. Okay, and to do that, I'm going to talk a little bit about, first of all, about selecting the lab and how you get samples and a little bit about the information that you can get from the lab. So let's talk first about selecting a lab. The first thing I'm going to ask you to do, and this is a hard habit to break, is to consider alternatives to your environmental laboratory. If you're a production company, you probably have some type of a relationship with an environmental laboratory. They do a very good job for you in analyzing water samples, compliance samples, and so forth. They're not typically the lab that's best suited to solve problems. They analyze lots of samples by known methods. They do it very well. They do it at reasonable prices. but they're typically not problem solvers. Material characterization labs, on the other hand, are just that. We exist, we have the instrumentation, we have the personnel, with wide variety of backgrounds to handle these types of problem solving, and the experience to customize the lab and consulting services for non-routine problems. Simply said, we're in the business of providing solutions rather than providing outputs. This will give you an example of some of the techniques that we're going to use. You see that there's lots of acronyms, lots of types of techniques that we're going to use here. Environmental labs are usually limited to those in green. They do a very good job typically at what they do, but they have a very limited scope that they focus on. Okay, so the first thing you might want to do is develop a list of lab candidates based on size, reputation, necessary geographical proximity. Now, geographical proximity might be important, and it might not. I mean, obviously we can take a scale in a jar and we can send it across the country to any lab in the U.S. in a day. Okay, but what if your problem is, and George is going to talk about this a little bit, Stephanie, what if your problem is bacteria? Okay, that are time sensitive, you've got to get it to a lab because the bugs are going to die. Okay, and you can get a completely different result. Or if you have a scale that's highly oxidizable. Okay, or in the case of ours, if the customer wants to send you 30-foot pieces of drill steel. Okay, not too many environmental labs want to deal with 30-foot pieces of drill steel. So, you know, sometimes proximity is a plus. And once you've identified some labs, look at their capabilities, see what type of instrumentation they have, see what type of experience they have in dealing with your type of sample. They should have a variety of personnel. The guy the corrosion guy is probably not going to be the same guy who's an expert in particle analysis. Again, you're going to have people that are experts in all different types of areas. Look at their client services. What type of working relationship do they have with their clients, and what type of relationship do they have that allows your input to be heard and to be considered in analysis? Because that's important, particularly in problem solving. You're the one that knows what your problem is, and you're most acquainted with it. Look at their quality system. If you have all these things up here, if they do sloppy work, it's still not going to be a very good choice. You talk to people who've used them, hear what their references are, see if they have a good reputation. And then, you know, consider cost. The cost is probably not going to be the lowest cost out there, as you might see from environmental labs, because we're solving problems again. It takes a little bit more time to do that. Okay, one thing I want to spend a little bit of time here is talking about obtaining a representative sample. This is unbelievably important and really shortchanged in the industry. Okay, so I want to take a couple slides and just work down through this. I apologize, the slide's a little busy, so I was going to go through it step by step. And when you're collecting solid samples, or collecting any samples, first thing I would ask you to do, if you can possibly do it, is talk with your lab, okay? They're going to help you through this. They're going to have a knowledge of how the samples should be collected, how much they need, all those details that will help them give you the best results in the end. It's much better to do that, if you can, take the sample and shortchange them on sample size, or that it wasn't taken in the right way, and then they have to consider, it raises some questions that they have to consider when doing the data analysis. You want to obtain a representative sample. Okay. These labs don't need a lot of sample. We can do an awful lot of work on a gram or two of sample. Okay, so a teaspoon. Or we can do an awful lot of work there. But the question is that teaspoon representative of anything? If you have sludge coming out of a pipe, and you take a teaspoon of that, is it really representative of what's coming out of that pipe? So you may want to take a little more sample, make sure that you have something that can be homogenized, that the lab can then subsample, and make sure it's representative of your process. Another good thought, don't alter the sample. Give it to the lab the way it is in the field, as much as you can. Don't grind it, don't dry it out. Try to give it to them as, the way that you're seeing it in the field. Minimize exposure to air. Some of these scales are somewhat air sensitive. I can tell you I've had situations where we analyze a scale in the lab, give results to a customer, I go out and sample the scale and get a completely different result because the scale is oxidizing. Take a sample, they throw it in a pickup on the seat, they run around for a couple of weeks in heat, give it to me, and by that time you've had chemical change. So try to expose it, try to minimize the exposure to air as much as you can. If the solids are slimy, and that's about the best word I can think of here. I mean, if you remember when we were kids, or some of your kids maybe have this stuff called GAC. If it looks like GAC, suspect bacteria. All right, and this is more prevalent, I think, in the industry than most people would like to admit. Again, collect the sample in a Ziploc bag. Prevent it from drying out. If it dries out, again, you have a chance of killing the bacteria. Okay. Try to get to the lab pretty quickly. Again, so that they can identify the bacteria that are there and give you an idea of what you have. If the solids can't easily be removed from a filter or a pipe, if you've got a connection, a pipe connection, or a piece of pipe with an end, just send the whole thing. Again, try to wrap it up. If you can't get it in a Ziploc bag, it's too big, put it in a garbage bag. If you can't get it in a garbage bag, put it in a drum liner. Try to give us the whole thing. If you can't get the scale out of it, we'll work with it. And sometimes it's good to actually see the whole thing and how it's adhering to the pipe and so forth. Provide some information about the process and the sampling location when you're talking to the lab. Again, we look at this as a partnership with our customers. If you give us some information, we're going to be able to give you more thorough results. We know what's important. We know what when we see things, whether to consider that, to go into it further and look at it in more depth, because we know a little bit about your process and how you took the sample. If you would note any health and safety issues, if there's chemicals that might be present on a scale, let us know that. If the scale might be radioactive, certainly want to know that as well. And then again, send it overnight. Don't throw it in your pickup and haul it around for a week, and then drop it off if it might be a different sample at that point. Sometimes you know you're having scaling, but you can't get to the scale to get a sample out of the pipe or out of a control valve or whatever. But you know that from a delta P across that area that you're getting some sort of flow restriction. If you can get a water sample, we can work with that and start giving some ideas to what might be causing the scale. Okay, again, if you're going to do that, talk with the lab. Try to get an idea of what they need to give you the best service possible. Collect the samples according to the EPA container volume, preservative, and holding time guidelines, and I put a link in your handout there. It will tell you, what type of samples to take, how much you need for different analyses, what preservatives to use, what type of holding times are critical for looking at those samples. Try to avoid putting things in pop bottles, empty pop bottles. Get pop bottles with a piece of paper towel stuffed in the top. Things like that don't really do well for sampling. Most labs will send you, if you can give them a little bit of notice, they can send you out some sample containers, maybe some that are preserved with the appropriate acids, so that as you get into the interpretation, there's no questions about what might have affected the data and what might not have. As you look through this, if you're looking at different analytes, you may have to collect more than one sample. For example, if you're looking at metals, you want to acidify the sample typically so that they don't precipitate out. You don't have iron hydroxides precipitate out, things like that. But if you acidify the sample, if there's TSS there, you're probably going to push some of the TSS in the solution. It's going to change your TSS concentration. Certainly going to change your pH, right? So if you're getting different analyses, you want to look at what needs done to fit the bill for each of those type of parameters. If TSS is a suspected problem here, try to get an idea of how much TSS is in your water. Okay, you can look at it. If it's a slurry, you know there's a lot of total solids in there. You're not going to have to take a whole lot of samples. But if you have a clean brine water on a treatment process, looks pretty clear. If the lab's going to look at that TSS and try to characterize it, you're probably going to have to give them a fair amount of sample. A small coffee cup type bottle of water isn't going to be enough. There's just not going to be enough TSS there to adequately characterize it. You might have to send them a 5-gallon bucket or a couple 5-gallon buckets so that they can get enough solids to work with. Again, provide some information about the process, health and safety concerns, and again, send it off to the laboratory as quickly as you can. The next part of the talk is to give you a little feel for understanding what information the lab can provide to help you resolve your problem. Now again, the lab's there to help with you, they're there to partner with you, but I think it's important for the customer to have basic knowledge of some of these techniques so they know what's available to them and what the lab has to offer so that they can as you're encountering these issues, that you know that there are ways that you may be able to get information to make good business decisions. Sometimes that can be pretty daunting. There's a lot of acronyms, there's a lot of different terms that are chemistry terms, that are not engineering terms you may not be familiar with. But again, what I'm going to do is go back to this roadmap that I put together for you and kind of lead you through some of this. Now, I'm not going to talk about some of these things in great detail. I have a lot of information on some of the slides that are coming up. I'm just going to talk just about the highlights of some of the techniques. If you're looking to characterize the scale in a deposit, one of the first things you need to think about is what kind of information do I need to solve my problem? Do I need to know what the composition of that scale is, or do I need to know something about the particle characteristics? Okay, so if you think you need to know the composition, the first thing you've got to ask yourself next is, okay, do I have an organic scale, an inorganic scale, or they're both present? And if you're going to analyze it. Sometimes that might be pretty obvious. If you don't have any inorganics in your system, then you probably don't have an organic contribution to your deposit or your scale. But if it's not obvious, you can ask the lab to run a real simple test, either a carbon or a loss on ignition. Try to understand, how much carbon's in the sample, and it will give you a pretty quick and cheap feel for what type of constituents there are in the scale. Once you figure that out, then you can follow this roadmap, this flow chart all down through it. Let's say that it's primarily an inorganic scale. The next question you want to ask yourself is, do I want to know what the mineral ID is, or do I want to know what the constituents are there and what their concentrations are? Most of these instruments aren't universal analyzers. You're not going to get all information from one technique. So you've kind of got to decide which it is that you really need. Do you want to know that it's calcium carbonate, or do you really want to know how much calcium and how much carbonate is there along with other constituents? If you want to know the mineral ID, then the next question is, how much sample do you have? Am I dealing with lots of scale here, or do I have a little bit of scale in water, that, you know, are a few particles that I want the lab to identify. And that kind of goes for these other categories as we go across. So let's talk first about trying to identify the minerals in a scale. The technique is probably best known for this, is X-ray diffraction spectroscopy. It's a technique primarily used for bulk solids. It requires a fair amount of sample. You get a diffraction pattern from the sample that you can identify different mineral types that are there. The disadvantage of this technique is that it's sensitive to amorphous materials, so they have to be crystalline. If you've got calcium carbonate, it's going to see it. If you have glass in the sample, you won't see it at all. Okay, it's got to be something that has a crystalline structure. The other disadvantage of it is that it's semi-quantitative. You can get some information, some quantitative information, more semi-quantitative. You can tell if there's a little bit, a lot, or a trace amount there. But it's not a real quantitative technique if you're looking for quantitation. Another technique that's less well known is electron backscatter diffraction. Okay, this is a technique that is used, detection techniques that's used with SEM that gets around some of the disadvantages of X-ray diffraction. With EBDS, you can actually look at individual particles, where you can look at very small areas on a pipe or a metal line and characterize the crystalline structure and so forth. The resolution, again, is quite good compared to what the X-ray diffraction is. Very good technique for looking at very, very small samples. Other techniques that are not usually considered for looking at inorganic scales or infrared spectroscopy and Raman spectroscopy. Infrared, you may be more familiar with. It's used a lot. Both of them are actually in organic analysis. And if you've got organics, you can take an infrared spectra that will give you a fingerprint of that organic. That works pretty well as long as, for inorganic or inorganics, as long as the mixture isn't real complex. But the more complex it gets, the harder it is for infrared to pick out individual compounds that are in them. It does have the advantage of being non-destructive, as does Raman. The big advantage of Raman is that it gives you a little bit more information on inorganic, but the big advantage is it's more distinctive and the resolution is higher. So with infrared, it would be hard to look at particulate. Raman, we can actually go in and look at 5 micron particles and tell you what the composition of that 5 micron particle is. The bad news for Raman is it's not very quantitative at all. It can be, but it's really challenging to get good quantitative information. This just shows what I was speaking of there. Here's a couple of infrared spectra for barite, gypsum, both sulfates, barium sulfate, calcium sulfate. You can see that there's some differences in the spectra, but quite honestly, the features here, the absorption features, are really in the same place. So you can imagine if you're just looking, if there's the only thing that's present is barite, you have a pretty good chance with this. If you have barite present, you have gypsum present, you have 3 or 4 other things in the sample, infrared gets a little bit complex to try to unscramble and tell what's there. Here's the associated Raman spectra. You can see barite on the top here, gypsum on the bottom. You can see how narrow these bands are. So it's much easier to resolve a complex mixture with Raman than it is with infrared, and it can be quite useful for looking at scales. Okay, other techniques that are used for looking at particulate can be optical microscopy. All the fancy things that we have in labs today, sometimes we ignore the simple things. Optical microscopy is pretty cheap, it's pretty simple. If you have a skilled operator, they can get an awful lot of information just in a real short time, just looking at the sample. And, you know, here's some of the type of information you can get. The other technique that we use a lot at our facility is scanning electron microscopy with energy dispersive X-ray detection. The thing that it gives you over optical spectroscopy is that you can get an elemental composition. So if you have a particle or a bulk sample, you can get elemental information. You can tell there's a lot of calcium in that particle or in that bulk sample, or there's a lot of sulfur in there, which helps you start leading you back to, you know, what the source of the scale is. The other thing that it does for you, it has a nanometer resolution. So you can look at extremely small particles. You can look at pores or sub-features within particles themselves, which can be quite important. And it has good depth of field, which probably doesn't mean much to most of us here, but to the microscopists in this room, what it says is, this is much easier to automate, because if I look at the top of the particle, I can see the bottom of the particle too. And so it's real easy it's much easier, I should say easy, but it's much easier to look at a lot of particles and characterize them. And I'll talk about that a little later. Another technique that you probably haven't heard much about is X-ray photoelectron spectroscopy. This is a technique that, you know, again, there's only various labs now. It's really good for looking at the top layer of material. So if you have a particle with a coating on it, or, you know, a metal particle with a corrosion inhibiting surface on it, if you want to look at the surface, or if you want to look at you know, a metal particle that's oxidized, and just look at the oxide layer and try to understand what's going on. This only penetrates about 10 nanometers. So instead of looking at the metal underneath the coating, you're just looking at the coating itself. And it gives you, again, elemental information. It gives you information about the chemical state, so you can tell whether it's iron 2, iron 3, this or so. Let's move on. If you're more interested in knowing how much is there, then if you're more interested in knowing how much is there as opposed to the mineral form itself, then these set of techniques here are much better for that purpose. Are much more quantitative. These are techniques you've probably heard of. These are techniques that environmental labs use pretty routinely. Mass spectrometry are complementary techniques that allow you to look at metal element concentrations in solids and liquids down to very, very low concentrations, up to 5% quantities. So it covers that whole range. One advantage of this is that it's matrix tolerant. If you've got a lot of things in the sample, they're probably less likely going to interfere with the analyte. And in the samples that you guys are dealing with, some of these produced water and so forth, you know, there's lots of stuff in there. So you want to have something that's real tolerant to complex matrices. Another advantage is you don't need very much sample. So if you have a water sample, we can filter the TSS out. We can take a look at the TSS, you know, from a chemical standpoint, as Steve was talking about. So X-ray fluorescence, very complementary technique, has the advantage of being non-destructive. So if you don't have much sample, you filter it out, you can look at that in an X-ray fluorescence spectrometer, then turn around and take that sample and use it for another analysis. Or an ICP, you can't. Once you've analyzed it, it's gone, it's destroyed. Another big advantage of X-ray fluorescence is you can analyze the solids. You don't have to digest them. So there's no requirement for the sample to be soluble in water or in acids. You can analyze the solids as they are. And another advantage, particularly in these situations, is it gives you a feel for how much halogen is there. You can look for things like chlorine and bromine with X-ray fluorescence. Those are not very well done by these techniques. Okay. The bad news is you need a fair amount of sample to do it, and the quantitation in complex and challenging matrices can be a little difficult. It's doable, it just takes a little bit more work. Okay, other techniques that are used for quantitation, if you have only particles, there's not enough sample there to look at by X-ray fluorescence or ICP. Even though they're very quantitative, they have great detection limits. If you don't have enough sample, you can't do it. Sometimes you can use scanning electron microscopy energy dispersive X-ray, look at single particles, get an idea of what their particle characteristics are. You can get elemental analysis, and you can piece these pieces back together to get a pretty good feel of what's in the sample. It's not going to be quite as quantitative as over here, but it may be enough to get you by if you don't have much sample. Okay. Another technique I'm just going to throw out there is ion chromatography. This is a chromatographic technique, obviously, that allows you to look primarily at aqueous samples. If you look at waters or anything that's soluble in water, it's extremely selective. So you can look at, you can determine chloride, you can look at sulfate, you can look at speciation of sulfur, you can look at, thiosulfates, sulfites, all type of anions. So all can also be used for cations, but rarely is, because there are other techniques that are a little less expensive that do this just as well. It's very quantitative, low detection limits. Again, a good technique for looking at these type of materials. Again, the problem is the sample must be soluble, and it should be pretty much water soluble. If it has to be acid soluble, it starts causing you some problems with the chromatography itself. You get too much acid in the sample. Okay. Thermal analysis is another technique that we use, so you may or may not be familiar with. Thermal analysis is a absolute method, which means you don't have to have a calibration. You're dependent on some absolute properties of the material itself. And what you're looking for is you're basically heating the sample up and looking at property changes as a function of temperature. And what you're looking for are things like phase changes that would occur as the sample is heated, maybe reactions that occur. For example, over here, what we're looking at, and what this scale here is 0 to 100%. You're starting out with 100% weight, 100% mass you weigh up. As you heat the sample starts to lose mass. And eventually, it will lose mass over a certain temperature range, which is this scale down here. And it will come back to stability again. This difference is quantifiable. And in this case, what you're seeing is calcium carbonate, as you heat it up around 650, 700 degrees, the carbonate will start transitioning to CO2, and you end up with calcium oxide and CO2. This difference is this weight of the CO2 that was lost. So you can then take that information and figure how much carbonate is. Okay? Some reactions don't have a weight loss, but they may have a heat gain or heat loss. It might be endothermic or exothermic. We can look at that, monitor the heat that the sample's given off as we change the temperature, and again relate that back to the type of change, the type of reaction that's going on, and the amount of heat that's given off allows it to be, again, quantifiable. These are very useful for looking at scales, trying to understand, particularly for things like gypsum, which can be present in a whole bunch of different hydrated forms. This can give you the type of hydrate there, to give you decomposition products of scales. You can get a whole lot of information from thermal analysis. All right, enough of that. Let's skip over. Let's say that your scale has an organic component. What you want to do is follow this route. Okay. If you have organics, one thing you want to do, or may want to do, is just do a bulk analysis on it. Look for carbon with a carbonate level. It's cheap, it's fast, gives you an idea approximately how much the sample is inorganic and how much is organic. That may give you enough information right there to tell you what you need to know. If it doesn't, you can use some infrared. We've already talked about infrared barometer to identify the different types of classifications of compounds in there. You'll know that they're polyaromatics, or either straight chain aliphatic or things like that that might be in the compartment. Is it oil, or is it some type of scale inhibitor or something else? Okay, I'm going to skip that slide right there. Go on to looking at composition again. If you're wanting to know quantification of the individual constituents that are in there, you may want to either use infrared Raman or use gas chromatography, liquid chromatography. Again, we've talked about infrared and Raman. We can do some bulk analysis. You can get a lot of information about the type of compounds that are there. Sometimes it's selective enough that we can tell individual compounds that are there and quantify them. It's non-destructive, so we can use the sample for other purposes. But if we really want to get really good quantitation, we're probably going to want to take that sample and do liquid chromatography or gas chromatography. It's highly selective. You can look for individual compounds. It's very quantitative. The detection limits are extremely low. So if those type of things are important to you, this will be the route to go. Okay, if you're more interested in particle characteristics, things like size, morphology, pore volume, those type of things, then we start looking at microscopic techniques. Okay. There is one other technique that we can use. I'm getting ahead of myself here a little bit, and it's a particle analyzer. There are different types of particle analyzers for looking at particle size distribution. Some of them are light-based, where you shine a laser on the sample, the particles diffract the light. From the diffraction pattern, you can get a particle size distribution. There are other ones that work on pore blockage, basically trying to fit a particle through a hole and saying, how many particles will fit through this hole type of thing. The advantage of this is it's pretty quick. You get a real highly resolved distribution. So if between 0 and 100 microns, you may get 100 bins of categories. But the problem with it is you don't have any information about what those particles are. You don't know whether the big particles are all one type of mineral and the small particles are all another type of mineral, or if they're even distributions. And that can be real important, particularly if you're starting to look at minerals plugging off filters or other media, membranes on RO filters, things like that. One way you can get around this is to do what we call computer-controlled scanning electron microscopy with energy dispersion X-ray. And basically what this does, if I can skip ahead a little bit, is you look at 300, 500, 1,000 particles, depending on how big they are, and you characterize the size, the shape, and the composition of each particle. And that's what we're looking at here. This is actually a flowback water. These are particles that are in it. And you can see these are individual particles. This is what they look like if under the microscope. You can see that most of them are quite small. This area out here is known as what it is. So this particle right here is almost all silicon. So it's probably a sand particle. Okay, whereas here's a particle here that's almost all calcium. That's probably a little piece of calcium carbonate, because we're not seeing anything that goes with calcium. I'm not seeing any chloride, I'm not seeing any sulfates, anything else. Okay. We can then take and get a particle size distribution by particle type. And you can see that here's your dirt sample, here's your sand, here's some barium sulfate that's in there, here's some strontium sulfate, calcium carbonate, and you can start getting a pretty good idea of what's in the sample, and you can get a particle size distribution to go with them, which may be important in a lot of applications. So, again, if you're just looking at, want to look at the particles, you want to see, tell a lot about how the surface of the particle, the size, the pore structure, those type of things. We can go back to optical microscopy, SEM, which we've talked about a little bit before. This will give you an example of the type of information that we can see. This is a polarized light microscopy image of a gypsum sample out of a FGD scrubber in a power plant. A good microscopist can tell you, which I'm not, can tell you what some of these particles are. Most of them are gypsum, obviously, but there's some things in here, calcium carbonate. I think that's a calcium. Is that calcium carbonate right there, Steve? No. Okay. So if you have a good microscopist, they can look at this and they can tell you the difference between different particles. The scale on this must have got eliminated when I pulled it into PowerPoint, but this particle right here is about 100 microns. This is about a 30 micron particle here. Okay, now here's a scanning electron map image, and I think that right there is about 10 microns. So this is about a 30 micron particle here. Okay, that's a 30 micron particle. The bottom line in SEM, you get some elemental information, which we're looking at down here. You can see real small particles. In this case, this helped us solve the problem because the problem was that they were having upsets on their scrubber. They couldn't understand why they were having chemical upsets. The culprit are these little round particles which are flash. So they're being flashed right through into the scrubber. Can't see them very well over here, but they're real obvious. This is a gypsum particle here, a gypsum crystal. These are all gypsum crystals on top of this polymer. But all these little particles are flash, which is causing problems for the scrubber. Okay. In summary, real quickly, you'll want to identify scales and deposits, understand the cause so you can eliminate it, so you can mitigate formation. I'm asked to take some time, choose an appropriate lab for the type of work that you're asking them to do. Take some time also and partner with the lab. Give them a sample, but give them some information. Work with them a little bit. If you do, you're going to get a lot better product from them. And again, I hope you'll use some of the things I gave you today to understand the strengths and limitations of testing, talk with the lab, and I think it will lead to you getting a more productive report from the lab for the types of services you're working on. Okay. I'm not going to go through this. It's in your packet. It gives you some ideas on the type of energy projects that we've worked on over the last year and a half. But I'd like you can see it right there. Okay, with that I end. Thank you.